Hello everyone.
Hello.
Hi Rohi. Give me 1 minute. I'm just running all the cells in my notebook. So I'll share my screen shortly. Let me just share it anyways because okay. So what we are going to do today, and I hope you can see my screen, is that uh, before we move on to the next set of regressions that we could do, we've already seen the techniques that we can apply to better our model. And finally, what we found is a set of 4 models. I personally like LM1 because that's where we got most of the accuracy. But let me see where the problem is. Okay, okay. So let me just quickly run all of these. Yeah, why was there an error? Mean squared error is not defined. Why? Why is mean squared error not defined? From sklearn model, no, metrics import mean squared error. Right. So let me just quickly run all of them. Yep. So what we have got is LM1 alt in LM4, and clearly, as per my view, I would personally recommend using LM1. LM1 is really good. I mean, any model giving an R square of more than 70 is really good for me because I've used those models in practice and they work well. They don't work really well, but that's not the objective here because, as you can understand, regression is where we are trying to do an estimation, not a prediction, right? So if you can estimate for 70% of the cases, that's really really good. So we have seen certain techniques to improve the model. We'll see two more. So we will create two more linear models, and then we will go into non-linear models because we are not here only to look into linear regression. We are here to look into regression, and there can be other forms of regression as well. So there are some other forms of regression. Let me just quickly write them down, and let me also tell you what they are. So other forms of regression, I can say, is going to consist of polynomial regression first. Okay, I say this because we are not going to do this. Okay, we are not going to do this because this is rarely used. Okay, this is very effective. I'm not saying that it is not effective, but it's rarely used. Okay, rarely. And the case is as simple as a regression model or any kind of model that you need to use or that you do use should be explainable, right? And polynomial regression, as you increase the sensitivity of the model in the sense of how much degree of the polynomial there will be, then it becomes a problem. So let me just quickly tell you what I mean by degree. So let's say I have, okay, so let's say, I'll just take this here. So let's say I have a graph which is something like this, and the actual graph, right? The actual data looks something like this. So I can call this a second order polynomial. There is one peak, and that's how we can identify a polynomial which is second order. So it will be something like this or like this, right? So this one or this one is actually second order polynomial. So it will have a function y equal to something where that something, let's say, it is dependent on x. So one of the x's will be square of x, right? There can be other x's as well on the right hand side of the equation, but they can either be x square or they can be x, but at least one x square will be there, right? So by the definition of a polynomial, one x square is there, so its plot is going to look something like this. Now Until this point, all is good. But then if we have a second order, let's say polynomial, so second order polynomial is this one, sorry. Then if we have a third order, let's say polynomial, then that might look something like this. Now, to explain a model which is something like this, where my x, my dependent variable, will be of cube or to the power 3, is really, really difficult. Even in this case also, it is really difficult. So imagine that this x square, okay, the square of this x that we have taken, this x represents the number of rooms, okay, the number of rooms, which is one of our features, right? So we are taking x as, or we're just assuming that, let's say, x is equal to the number of rooms in the dwelling. So you can clearly imagine, if I have an equation which is y equal to 1.23, let's say, y equal to 1.23 x square, or I can even write it down, let's say. So let's have an equation, final regression equation of 1.232 x square plus something something something. Then to explain this is really going to be difficult, is because if x is the number of rooms, let's say, how do I define x square, right? Because x square can be a mathematical entity, right? Mathematically x square exists, but how about in practice? Can we have something called x square? The answer is no, right? In some cases it might well apply. I'm not saying it won't apply. So let's say if I have a variable that I can really control, like I'm in a factory where I'm one of my features is, let's say, the amount of uh, machine oil that I'm using to grease them, right? And then I have to predict what is going to be, let's say, the daily production numbers, how much items I'm going to produce every day. In that case, if I have, let's say, the oil represented as x square, I may still be able to, right, to represent it, because it's a volume and I can really represent it. So in some cases it may well work, but in many other cases it doesn't work, because the features that you see over here are not attributes, they are the properties, right, of the data, of the setup. So it's really difficult to explain a polynomial regression, and that is the reason why in industry we all know that we can do that, but we seldom do it. Now there are two more forms of regression. One is called rig regression and another is called lasso regression. I'm going to explain them to the best of my efforts, but not right now, because we are not done yet. Okay, we are not done yet with the linear regression that we were doing. As I said, we'll do two more models. Then if we have times, we are going to look into these three as well. I believe we'll have time, but we'll try to cut the session short because I have some other things to attend. So maybe we'll keep the session a bit short for today, and maybe we can extend on, let's say, Monday. Yeah, I hope that's fine. So now what I would like to do is that here I would just like to play around with a certain thing that we have not played around with. So what I'm going to do from sklearn dot pre-processing, I'm going to import min max scaler. This is another type of scaling, right, that we do. Now let's just quickly look at what is min max scaler. If you simply do min max scaling, you will get the results. You will get the results here, right? So here is the formula. Clearly, the formula is x is equal to x minus min by max minus min, which means I'm subtracting the minimum of x from x. So I'm subtracting the minimum of x from the value of x, and then I am actually dividing it. I'm actually dividing it by the range of x. Okay, so that's exactly what I'm trying to do, right? And that is what is known as min max scaler. So this is a very good way to normalize. Okay, so this rescaling of values applies on any numerical data that can convert it in the range of 0, 1 or minus 1 to 1, right? So selecting this range, the general formula for 0 to 1 will be this, right? So min max normalization is very simple to understand, but let's see if in our case it's really going to help. So let's say I'm going to create a min max scaler. So min max scaler MMS is equal to min max scalar, sorry, right? I'm going to create an object and I'm not going to pass anything within it, right? Now what I would like to do, I would like to take one model which has all the data, right? So I'm going to take one model which has all the data and one model which has our reduced features. So most probably LM1 and LM3 are my good candidates. So let's just quickly look at what values were taken in LM1. Okay, let's go up and we're going to find LM1, right? We are going to find LM1. I believe it should be somewhere around here. Yeah, it is here. So for LM1, we have these X-train 1, X-test 1, and so on and so forth. Okay, we have not scaled them. Okay, but we will be scaling them now. Where is X and Y? X and Y is taken from where? X and Y in this case is taken from the Boston dataset itself, not from Boston final data frame, which we created. So I'm going to take the Boston dataset once more, and I'm going to say, what are the columns? So these are the columns, and I'm going to take X is equal to the list of these columns, which I'm going to put over here. And then I'm going to simply do this, and Y will be equal to my MEDV. Now I have X and Y, and what I'm going to do is X scaled 5, right? Because this is my fifth model, so I'm taking X scaled 5 is equal to min max scalar dot fit transform, and I'm going to pass X, right? Now it is saying could not convert string to float. CRIM is a string. Why is it a string? Oh, okay. So I did this mistake. I've done this mistake twice actually. It should be here, and Y should be Boston, and this. Now it should work, right? So it has worked now. So I have scaled this X, named it as X scaled 5, and I am scaling it using min max scalar. Now what I'm going to do, X train underscore 5. I'm just going to copy this part so that it is easy. X test underscore 5, Y train underscore 5, Y test underscore 5 is equal to train test split X scaled 5, comma, Y, comma, random state is equal to 101, right? Give me 1 minute. Yeah. So now I have got the training and testing splits. So let me just quickly check them. As of course, I always check the size, right? Although this is not really required, but it's good to have. Yeah. So let's quickly check that. Y train shape and Y test 5 shape, right? So it's in a good shape. Now I have done a min max scalar. Let's just quickly look at X train underscore 5 and see what it is doing. So it has converted the values in a very small range. Okay, so I believe the range will be something like 0 to 5, but let's just look at it. X scaled 5 dot describe, right? But it's an array, so I cannot do that, right? I cannot find the min and max, which is fine. Maybe I can take the first row, right? And I can try to find the np dot mean. Np is not defined. Okay, so I'll import numpy as np, and np dot mean is 0.3. Np dot median of X scaled 5 1 is this. Let's say it's in a quite good range, as you can see. Np dot standard deviation. Standard deviation is X scaled 5 inside brackets 1, right? So it's a very well kind of a defined kind of a graph, right? And we have really taken that quite well. So I think this should work. This should not be a problem. So let's take this and let's go ahead and fit our model. So we have train, test, split, everything we have. right? So now we are going to fit our model. So now I'm going to say LM5. So this is my fifth model. So I'm taking LM5, linear regression. When I got this, now I'm going to say LM underscore 5 dot fit, and it will be X train 5 and Y train 5, right? Now what I'm going to do, I'm going to do the prediction. So Y pred 5 will be equal to LM5 dot predict X test 5, right? So I've got the predictions. Now obviously I'm going to look at the coefficients. So let me just quickly look at the coefficients. I know how to look at the coefficients. I'm not going to waste much time writing it once more. I'm just going to do a copy paste. So these are the coefficients that I've got. You see the coefficient values are now really high because you have scaled it with min max scalar. Now your coefficients will be really strong or really low. So it can really go up to, let's say, minus 21. Here you can see. And the plus values can even go up to plus 18, right? But this is nothing to be scared of. Okay, LM-5 dot intercept will also be a good standard kind of a value. This may not change much, but let's now look at R2 score. Okay, R2 score of Y pred 5 as opposed to Y test 5, right? My R square scored is 60 or 0.58, and my mean square error is Y pred 5, Y test 5, and this is equal to 30.11. So this is almost similar to this one, right? This is not really very good. We have not achieved anything much over here, but it's good that we have tried, right? So RMSE comes closer to 30, I believe. RMSE is what, closer to 30? Yes. And then R2 is closer to 59, right? So not very good, but not very worse as well. So this what we have done, min max scaling, and I'm going to write all features, right? So this is how it is, right? So we have used min max scaling by using all features. Just a moment. Okay, so these are all reduced features, right? So I will take this and put it over here and put it over here just so that we understand. Okay, so we got 5 models. Now we see that even in this case, my first model is really, really very good, right? Really very good. Even if I have done the RFE, my first model is really very good, right? So really good, no problem. Let me just see RFE, RFE dot. Just a moment. Give me 1 minute. Okay. So let's not use the RFE columns and let's not create one more. I mean, we have already tried a lot of models, although we should do that 6-1, but I'm simply skipping it so as to save some time. But our final conclusion as of now, without trying anything advanced like a ridge and a regression and polynomial, a polynomial I'm not going to try. Right, polynomial I'm really not going to try because it's really not really required, but I can give you links from where you can try, right? So that should not be a problem. I'll post it on our group. Okay, but it's really not much used in the industry because, as I said, to define the square of a feature is really, really very difficult. It's like to explain that I have taken a square of a variable, that to a person who is working in business, is really difficult, right? Okay, so we have reached until certain point. Okay, so let's now go ahead and look into the other cases. Okay, the other cases that we are going to look into are my ridge and lasso regression. So first of all, let's look into ridge regression and try to understand what is ridge regression or what is lasso regression, and then we will try and understand what is going on over here. Okay, so ridge regression, in a very simple words, it's also known as Tikhonov regularization or Andrei regularization. So I'm just going to write this over here. So regression is known as Tikhonov or Andrei regularization. I might be doing some spelling mistakes here. Maybe Andrei ends with Y, but that I believe is fine. So it's a regularization method mostly used in cases where we have we have uh, um, co- multi collinearity problem with the data. So for example, if you have a data which is like ours and there is a multi collinearity problem where there are multiple features related to other multiple features and you are not in a position to get rid of any one of them, just like we did not do, right? We took all the features, right? If you look at our model, LM1 being the best, it has taken all the features irrespective of whether or not there is any intra correlation between two or more features, right? So we have not considered that scenario at all and we have built a model, which is not bad, because even after having a multicollinearity, if we are getting good R square value and lesser RMSE, that's all we want, right? We need less of errors, more of the variability to be explained, and that's exactly what we are doing, so no issue, right? But how ridge regression works, okay, can be explained. Let me just do some drawing and let me just explain this to you. uh, ridge regression, you can say, is when, okay, or maybe I'll start it in a different way. Regression is where the number of the predictor variables, okay, in a set exceeds the number of observations, or in other words, it has multicollinearity. Now, in our case, when we are doing ordinary least square regression or when we are using gradient descent, right? So it is not really built for cases. It has the mathematical issues. Sorry, I think by mistake I pressed something. No, but it's still working. Right. So ordinary least squares or our gradient descent problem fails to work when we have these kind of predictors in the model, right? And then of course, unless and until we are doing RFE and VIF, they out of the box do not talk about important or less important features in the model. So ideally, if we do not do any such kind of exercise, which by the way did not help, so just a moment. Okay, so in case of ridge regression, what we do is that it works in part because it doesn't require, okay, it does not require unbiased estimates, right? So any estimation that it does is not biased with respect to the multicollinearity or any such kind of problem which might be there in the data. Now, how does it do that? Is by using a concept known as ridge estimator. Now, what is this estimator? Okay, this ridge estimator is trying to estimate the true population parameters. So why we are saying this is because the data that you have, or that matter, the data that you will anyways be using to do modeling, will always be a sample. Even if we have done training and testing sets out of it, it's always a a subset. Okay, it is always a subset, right? Why is it a subset? Is because we can't get all the data, right? I mean, we do the modeling on a very selective set of data, which is the representation of the population. And then we use that to create the model. Once the model is created, then we use the model on top of the real life data, right? So let's say I have hundreds of GBs of data. I don't use 100 GBs of data, right, to create the model. The data that I'm using over here related to Boston house price, this may well be a very small part of the data, right? It's not really a very big part of the data. It's a small part of the data which we have used to do the modeling. And I have tried my level best to ensure that this small set of data is a good representation of the population. Now, what happens in case of ridge regression is that it uses a type of estimator, otherwise known as a shrinkage estimator or a ridge estimator. So I can write it down. Shrinkage uses shrinkage or ridge estimator. Okay, and the purpose of this estimator, right? The purpose of this estimator is to produce, which produces, okay, new features or new estimators within or from the data, okay, from the data that shrunk closer or met closer to the true population parameters. Okay, how does it do that is the question. How is it able to understand? How is it able to understand the features that we have to take and then extract the features from it? So what it is trying to do is it is simply trying to find out some meaningful features out of a set of features. Now, how is it doing that? How it is doing that is a technique otherwise known as regularization. So regularization itself is a technique. So technique used in point number 2 and point number 3 is known as regularization. We'll look at this regularization thing from time to time, but as of now, I can tell you there are two common types of regularization known as L1 and L2. Okay, we will go in depth about what is L1 and L2, don't worry. But as of now, for our simplicity, we will say that L1 and L2 or any form of these kind of regularizations help me control my model, right? So that they don't go out of bounds. They don't grow beyond uh, a situation where it is difficult for me to control the variability in the model, or I'm not able to explain much of the model and so on. So in short, regularization is simply a technique to penalize the errors in my model or penalize those factors causing errors in my model as much as possible. So the ultimate goal of regularization is penalize the errors or factors causing the errors. Right. So what I mean by this is my final goal by means of doing regularization is to decrease the value of RMSE as much as possible. And in turn, if there is any way, I'll try to increase the R square value. And that's exactly what ridge regression is trying to do using a method known as shrinkage estimator. Now, again, the question is back again. How do I do it? Right? How do I do that? Right? How it does that is it creates, okay, a correlation matrix or an estimation coefficient matrix. And then it tries to add a new parameter which is known as K. Okay, adds new parameter in the model represented as K. So what I mean by that is earlier my model was what? My model was as simple as y equal to some theta 0 plus theta 1 x1 plus theta 2 x2 and so on and so forth. So this was the mathematical representation of my model. Now what I'm doing in this entire model, I am adding a new feature which is K. Right? I'm adding a new value which is K. A new weight you can call which is K. Yeah. And then I'm multiplying that K with an identity matrix. If you remember when we looked into the basics of matrix algebra, we talked about identity matrix. So adds a new parameter in the model called K, okay, multiplied with an identity matrix, right? Now we have to define the value of this k, and basis the value of this k that we define. Okay, and I'm just going to add more to the confusion. This k is also called alpha, as we will see. Not called, is also represented as alpha in many cases. For example, in sklearn, the library that we are going to use, right? There also, in case of ridge regression, the hyperparameter is not k, right? It is not k, it is actually alpha. But it is represented as alpha, right? So it is basically the value of k only, just the name has changed. Now, the reason why we are doing this multiplication of k with an identity matrix is to identify, okay, identify or get a tabular outcome of values which represents which weight is of more importance, or the combination of which weights are more important. If you can try and visualize this. So if I'm able to create a data set out of my features data set, so these are my features, and from these features, if I can give, let's say, a big square value over here and a small square value over here, then what I'm simply trying to do is I'm trying to mark this column or this feature, right, with a bigger X, indicating that this feature standalone is a rather more important feature than this feature, right? So this is the overall work which this K is trying to do. K is not giving the thetas. K is trying to give the importance of those thetas when multiplied to X. So we have a formula, we have a mathematical equation which says y is equal to theta 0, right? Y is equal to theta 0 plus theta 1 x1 plus theta 2 x2 and so on, right? So what is the importance of this theta 1 x1 is given by one value in that k multiplied by identity matrix. So one value in that matrix will give a weight to this feature or this combination, this multiplication output. And then we get another value for this, we get another value for this until we reach the end, right? In this way, what ridge regression does ultimately is that the one which has the greater weight, right, will be considered in the modeling part, while the rest will be silently ignored. Okay. What I mean by silently ignored is that you will not be even be able to come to know that they are ignored while creating the model. So in the background, it also depends on which library you are using. sklearn, as I have already told you, it's a black box. So you won't be able to understand how exactly we are doing this, but in the background, ridge regression implementation is going to apply importance towards the features using the value of alpha, right? Alpha. Okay. And this is hypothetically, okay, not a mathematical statement. Mathematically, there is a different way to represent this, but we are not going to go into that kind of a complexity right now. So if anybody asks you what regression does, so you need to understand it as a regularization technique. A regularization technique is a method by which we penalize the errors more and more so that it doesn't increase beyond leaps and bounds. And we try to do this by controlling the factors which are causing the errors. While in part of ridge regression, we are using an estimator known as ridge estimator, which is helping us to create new estimators from the existing data by making use of a value of alpha. Now we don't know what is the value of alpha going to be. We really do not know that, and we are going to find out. We may create 2 to 3 models and try different kind of alpha values and find out what is the best value of alpha for my model, because the one for me will not work for you. For example, if you have a different kind of a data set and I've selected a value of alpha which is equal to 1, right? And you have a different kind of a data set where you have selected a value of alpha equal to 1 because I have used it in my model. That does not mean that your model is going to perform better. It may well be the case that usage of ridge regression does not even help improve the performance of the model. But usually it is seen that regularization helps to increase the performance, but it's not a guarantee. It's not a guarantee. These techniques, right, point 2 and point 3, these are simply extension of linear regression. In the background, you are doing linear regression only. Some features, some factors are getting added on top of it. Some new functionality is getting added on top of it, on top of the algorithm, and that is helping you do two things, clearly two things, otherwise known as regularization. You're trying to decrease the error, right? You're trying to decrease the error by giving more and more importance to weights or to factors or features which are not causing the error, right? I hope until this point in time it was clear. Let's look at the practical implementation quickly. So for this, again, from sklearn, I'm going to import the library, right, so that I can do the regression here. So I'm going to say from sklearn.linear model, import ridge CV. No, ridge, right? I'm just going to import ridge. Then I'm going to create an object, and then I'm going to create the ridge model, as simple as it sounds. Now, let me not create one model. Let me create three models. One with one value of alpha. Okay. So we are going to create one with one value of alpha, and then we are going to see how it is really uh, affecting the model. Okay. So let's create an object. Ridge is equal to ridge. Okay. So why ridge? This is also a linear model, right? So LM6. I'm just going to say LM6. We have done until LM5. Just to keep the naming convention, right? I'm taking a new ridge. I have not given it any value of alpha. Alpha I have not selected. K value I have not really selected. Okay, let it take the default value. Let me fit the model. Let's see how it works. Okay, what I'm going to do again, I'm going to create my X and Y is created already. Okay, X and Y is created. Right, just now we have created X and Y. We are not going to waste time in there. So what we are going to do, X train underscore 6. Right, now we have underscore 6. So X test underscore 6. Y train underscore 6, y test underscore 6 is equal to train test split x y random state, sorry, random state 101. Right, let's skip the step of looking at the shape. We already know what the shape is going to be. If you want, you can run this once and check the shape as well, but you know what is going to be the output. Let's now try to fit this model. Right, so what I'm going to do, lm6 lm underscore 6, I'm sorry, dot fit, right, dot fit x train y train. So we have fit a model x. Oh no, I'm sorry, this should be underscore 6, right? So now you see it has selected a default value of alpha equal to 1. I did not say, I did not ask it to select a value of alpha equal to 1. It selected a value. Clearly it selected a value equal to 1. Okay, this is the most important hyperparameter. The rest are not that important, hence we may really not delve into them. But if you look at the documentation, you'll find the details. But the most important is the value of k, because that defines that k into identity matrix, right? And that k into identity matrix will ultimately give the valuation of the weights multiplied with the features. So the value of alpha is really critical, but I have not really given any value here, and it has fit me the model. Now I'm going to see the predictions. Y pred 6 is equal to lm underscore 6 dot predict x test 6. Right, now I'm going to get the R square score of y pred 6 as compared to y test 6. Right, you see the R square score is really not good with this value of alpha. With this value of alpha, R square score is really not good. What about the mean square error? Mean square error of, again, I'm just going to do a copy paste from it so that we can repeat the exercise. It's near to 30. So I have again got another model similar to LM5. Okay, now let's try to change the value of alpha. Let's say alpha is equal to 5. Right, and now I'm going to fit a new model. Okay, so how am I going to do that? I'm going to take this and I'm going to select 7, 7, 7, 7. Right now I'm going to say linear model 7 is equal to ridge, and alpha is equal to alpha. Right, so alpha is equal to 5 I have first. Now I'm going to say lm7 dot fit it to my x train 7 and y train 7. Now I have fit the model. Alpha is equal to 5, as you can see over here. Right, now I'll get the predictions. Y pred 7 is equal to lm7 dot predict x test, and I'm going to select 7 here, and I'm going to look at R2 score. Y pred 7, y test 7, and the value is 56. What was the earlier value? 57. Now the value is 55. It is decreasing. So increasing the value of alpha is decreasing the value of R square score, right? So we see that if we increase the value of alpha from 1 to 5 as in above case, okay, the R square value is actually decreasing, right? So which is wrong, which is really not good. So mean square error, although we don't really need to look at, but let's just quickly look at it also. Mean square error will not be very good. It has increased a little bit. You see 31 it has become. Now we are going to decrease alpha. How? I'm going to say alpha is equal to 0.001. I've really taken a very low alpha value. Let's see how this guy is going to work. I hope you are able to understand, right, what we are trying to do over here. We're simply selecting some ways to randomize the values of alpha, and for different values of alpha, I'm trying to see what is my output. At later stage, this is too early. I'm going to show you a grid search cross validation method. It's a very, very useful method to automate these kind of things. I run grid search, it will automatically tell me, okay, you have to select a value of alpha is equal to this, so that you have a very stable model. You're not doing it right now because that is simply going to confuse us and make us lazy, right? That's why we are not doing it right now, although we already have a methodology to do it, right? So now what I'm going to do, I'm going to fit my eighth model I'm going to fit. I now have a very, very small value of alpha. Why I've selected this? Because my assumption is this. My assumption, if I increase the value of alpha from 1 to 5, my R2 value is decreasing. So if I decrease the value of alpha, I expect R2 to increase. That's a very layman kind of a thing, right? I mean, just like a kid, I'm trying to expect more and more value out of my model. But I really don't know whether this data and using a ridge regression is really going to help me or not. But let's see. I mean, there is no harm in trying, right? Now let's see the R2 score, and then we are going to pass ypred 8 as opposed to ytest 8, right? It does not change much from the last value. From the first value, which was like 57, it went up to 58.8. Will it really matter if I choose a very small value of alpha? Let's see. No. See this? If I change the value of alpha now, the value doesn't change much. Right? 0.01 also, it is 58. So without using any scaling, and by using all features, in our use case, ridge regression did not work better than a linear model. Okay, this indicates that we do not much of non-linearity in our data set. Had it been the case, then the ridge regression would have worked in a better way, but it did not work. right? At least the values that we have selected, it did not work. Okay, let me try one more time. Let's see if it is giving anything better. The answer is no. It's not giving me anything better. Is it giving anything better with a very high value? Let me try 100. Huh? See, the more I increase it, the R-square score is decreasing, right? With 1, it is 57. With 0.1, let's see what is happening. It is 58.61. What about 0.5? 57. No, there is not much change, right? So I'm not able to increase the R2 score of my model by doing changes in the value of alpha much. So clearly, ridge regression is not a use case to be applied over here. That is one of the two things that I wanted to share with you. First is the definition, and the second is just because of above, it's not always better than a linear model. Okay, it will be better. It will be better if we have good amount of non-linearity within the data. Okay, examples will be too much non-discardable features in the data which are not linearly related with the outcome variable. Okay, so I hope you have understood what I'm trying to say over here. So if we have a data which is really complicated, lot of features are there, they are non-linearly related with the target, with the output. Ridge regression may have been a better use case. For us, it's not a good thing to do, right? We have done some models now with ridge regression as well. It didn't help, right? We are going to take a stop now. As of now, we'll continue from Monday, but I would request you to read about ridge regression. If you have any questions, any doubts, any queries, if you find, please do let me know. We are going to discuss that as well. But let's continue from Monday. On Monday, we will quickly look into lasso regression, what it is. You may want to study in on the Google what is the meaning of that word lasso. But if you have used softwares which are for image processing, you may already know the meaning of that word lasso. You may have, or you may have used a lasso tool in case of you know cutting down the images or processing images, usually in softwares like Photoshop. We are going to take that ideology and try to define what is a lasso regression. Okay, because the tool which we are going to use, or the method that we use to do a lasso regression, is not exactly but relatable to that lasso tool which we see in any image processing software, right? But let's continue in the next session. I'll stop the sharing. If you have any queries, Rohit, please do let me know. Yeah.
Okay. Thank you.
Thank you. Good night. Thank you.
Good night.